Hi sir, as I had mentioned to you in the last video that this video would be about proving the same hypothesis that in the case of the cadmium selenide, which is doped with, as you see, with iron and one cadmium vacancy, if it is neutral, then I had shown based upon the charge density plots that this Fe has to be Fe3 plus and not Fe2 plus. And to do that, what I had done was I'd compared the charge density plots and I'd shown you the charge density plot for Fe3 plus without the vacancy, Fe2 plus without the vacancy, the neutral cadmium vacancy, and the Fe and the cadmium vacancy for the neutral cadmium selenide, and then we have the charged one. So in the case of the neutral one, which is the point of discussion, we see over here, and this was what I had used, the charge distribution, to state that this is Fe3 plus and the cadmium vacancy. Now the cadmium vacancy won't be neutral because, as you see over here, that there is charge distribution around it, and the same thing we had seen in case of the neutral one. The neutral structure, the cadmium vacancy itself has some charge distribution around it, and the Fe3 plus has the same charge distribution as the one that we're seeing over here with the vacancy. So based upon that, I had stated that this is not Fe2 plus at this point, but Fe3 plus. Now I'm going to be using the density of state plot for the same ion with the cadmium vacancy and ion without the cadmium vacancy, both with the neutral and the charged structure. So we are comparing these two structures, the cadmium selenide without the vacancy, that is this one right here, cadmium 89 Fe Se90, and we're using both the Fe2 plus and Fe3 plus. Even though we are calling it Fe2 plus and Fe3 plus, it's basically supposed to be a structure that is neutral and charged. So therefore a charge of +1, and the neutral one, the same thing for the one with the vacancy, neutral one and the one with the charge of +1. So we're doing the site projected density of states for Fe in these four cases and comparing them. So if, based upon my hypothesis, if the site projected density of states for Fe, but Fe with a charge of +1, let me just write it in the proper way so it'll, okay, charged. Charge +1, if that is the same thing as neutral, if they both have the same density of states, then we can say that this is supposed to be, this is supposed to be Fe3 plus and not Fe2 plus. So now we're going to compare them. So I have the site projected density of states that have been that I got from the VASP calculations. So I'm going to start off with center being compared to, right. So I'll start off by first comparing the neutral and the charged. So here I'm starting off with the d orbital. So I'll start off with the d orbital and 7d, right. So as you see, the d orbitals, oh, sorry, that was my mistake. I used the wrong one. So I'm supposed to do center. So I'm starting off first with the s orbital, my mistake. So with the s orbitals, as you see over here, there is a difference. You see that there is the density of states are different at the same point, even though the energy is the same, but the density of states are different. So the purple represents the neutral one, the blue represents the charged one. So this is the blue and this is the purple. So you see the difference between the blue and the purple. You see the definite difference in the density of states, even though the energy is the same. The density of states, the density of states, they're different. So this was the S. Now we go off to P. Again, with the P2, we see the difference. You see over here, the difference right here. The blue is for the charged one, the purple is for the neutral one, the same thing on this side, the same thing over the HOMO-LUMO gap you see over here, or we can call this the band, the valence and the conduction and gap. So in the conduction band, you see the difference in the density of states, even though the energy is the same, and in this case, almost the same. So again, over here, we're seeing the difference. So it's not exactly the same. Now we go for the d orbital. So again, with the d orbital, we see the difference. So we see the density of states. You see that there is some difference. Now the blue one is for the charged one. The purple one is for the neutral one. So you see the difference on this side and this side of the band gap. So by this, we can say that it is not exactly the same oxidation state for iron in the case of the neutral and the charged structure with the vacancy. Now, I'll compare the substitution without a vacancy, but the neutral one. So I'm comparing both neutral structures. And I'll start off with the, I'm starting off with the S. So this is cadmium selenide with a vacancy and iron, but neutral. This is cadmium selenide with iron substitution, but neutral. And we see over here the difference in the density of states. The density of states is also different, but also the energy is also different. So the energy of that state, as we see, they're different. So therefore, the S states, they are not the same. Now let's go over to the P state. So the P state too, we see that has shifted. It's not exactly the same. The energy has shifted. The purple being the one with the vacancy, the blue, the one without the vacancy. So we see the shift. Then we go for the d orbital. Again, we see the same thing. It has shifted. We see in case of this right here shifted, right here shifted, the same thing right here, the same thing right here. It is shifted. So it's not exactly the same. And here we see the density of states itself is different. Now we'll go to the final one where we have where we're using the charged one. And we'll start with the S state. Or let's start with the D state. So we're starting with the D orbital. So this is the D orbital. And in this case, as you see clearly, that the density of states and the energy at which we see the density of states, they're almost exactly the same. So this one, as you see over here, is the cadmium selenide doped with iron without a vacancy, but the charged one, charged with +1, so one electron has been removed, which we concluded is Fe3+. And this is a neutral structure, so with the cadmium vacancy and the iron. So as you see that the S states, they're almost the same. So now if all three orbitals, they're almost the same, then that means that in this case right here, what we have is Fe3+ with the vacancy. Then we go off to the S. So we looked at the d orbital, now we're looking at the p orbital. Yep, and that too, right, that too is almost the same. As we see, it's not such a huge difference, but it's almost the same. And the difference, so it's almost the same compared to the other two cases. And then we go off to the s orbital. So this is our s orbital, right? Let me the right place. Yes, again, even this too, it's almost the same. Now let's look at the total of everything. The total would be the total of all the states, 9, 8, so here is a combination of all of them, and we see that it's almost the same, but again, you see over there is a slight difference in the density of states in these points right over here, but still it is almost the same compared to the rest of the ion substitutions. So based upon this, I'm making the argument that it is Fe3 plus at that location and not Fe2 plus or any other oxidation state of iron at that exact location. And I'll be sending you all these images so you can also personally look at these images. Thank you, sir.